So, talk to me. Is there any immediate issues that are going on? Are there any issues there about the lab? I don't want you guys to stress out too much about the lab. All I'm looking there for you guys to do is just to look back upon the physics course. And you know what? I'm not even going to keep it to my physics course. If it's any physics course, anything, I don't know. If you don't know if it's not enough physics, shoot me an email. We'll talk. And like chemistry is physics, biology, mucho physics. They're all interrelated. I know we teach them kind of separately, but like this is not my biological hand, and all this is my physics ear. It doesn't work like that. So what I'm looking for you guys to do is just to find something there physics related that you can do an experiment with. There's 100 gazillion physics experiments on YouTube and all that. Find something there you like, reproduce it in some fashion, make it your own, have some fun with it. Yeah, you have 2 weeks to do it. I'm still trying to work out. I would like to have video because video, is easy. And do we have to make a good question there, Joanna. What I envisioned was, you partner, I don't know, family member or somebody videoing there, and you make a little video, you snip it and put it all together, and you introduce your topic. The physics of blades of grass. Don't do that. All right. And the history, the gray blades of grass have been studied there for hundreds of years, and the interesting physics behind them there, and just a little bit of historical backgrounds. Anything, just to kind of introduce myself or the viewer to your topic. You would do your experiment, and then at the end there, any type of physics equations or maybe a little mathematics or applications there to society, futuristic, these kinds of things. And I envisioned a video because, it's a digital age, right? And I just don't know how to upload them. I don't know. You guys tell me. Are you able there to send me a link that I can go and view? I don't want to intrude on anyone's privacy, but we'll work. And at the very least here, probably what we're going to be looking at is a PowerPoint. All right. And I would like to keep it like a PowerPoint. If you wanted to do a paper, go for it. And I'm just trying to think about what's easier there for you guys. And this paper or PowerPoint will have lots of pictures in it. Okay? With every picture, there'll be an explanation of what's going on. It should be kind of sequential in nature. Introduction, experiment, kind of a discussion, relevance at the end, kind of a thing. And so I'd like a video, but I don't know if Blackboard can handle. Like, what's a 5-minute video? What's that? 70 megs, something like that, times 30. I don't even know. Probably the Blackboard Georgian hard drive is probably 1 terabyte. That's it, and we'll load it out with a couple of videos. So I don't know how it's all going to work. At this point in time, my Blackboard guy hasn't got back to me. When they do, I'll update you. But we're probably I'd like to have video, but we're probably looking at a PowerPoint that you would hand in. And someone was asking me about how much. Well, I don't know if you could really do this justice if you had 5 pictures. 1 picture, and all this kind of stuff. So I don't know. I'm not going to give a length. At the, if you watch your video or watch your PowerPoint or read your paper, is it full? Is it, and what I mean by full, is it rounded? Is there a start, a middle, a beginning? Does they kind of tie in together? Is there lots of pictures? Is the science relevant? And, these kinds of things. So I don't want you guys to break your nose on this, okay? I know you guys have got lots going on. So have some fun with it. Get a lab partner, coordinate there, and see what you can come up with. You guys, this is one of the best classes I've had. You guys are right on top of things. Like you guys are just banging out these exams. Class average, I think, is 80. Like, it's just, you guys are good. Keep on it. Your final test is in 2 weeks today. Okay, and what we're looking at is a 3-hour test. That's what we're going to look at. And we're going to look at from 12 till 3, 2 weeks there from today. Okay, and what we're so we had last week's hello. Oh, thank you. You saved my life. Thank you. Oh. Wonderful. Oh, did you make it with that soy milk? Oh, thank you. Anyway, I can't even drink that. All right, so what we're looking at is a 3-hour test. You'll notice there that last week and this week here, which we're going to go over right now, and next week, it's not heavy on formulas. It's not at all. Okay, sorry I missed it. Okay, all right. Joanna, I'll get your question there in a second. As far as makeup questions, we're looking for a little bit of everything there. The test is a comprehensive of just new material. The test will just be on last week's electricity. Hopefully the assignment is going okay. I wanted you guys just to focus on electricity because I think that's where, that's the only math component, basically. This week's and next week's, it's more just subjective. It's information based. You'll see there that there's a lot of terms, new terms. Okay, so this last test will not be mathematically focused. All right, so we're gonna have it in a 3-hour time period from 12 to 3 there, 2 Mondays from now, and I don't think it'll be that bad at all. Okay, but we'll have a look at it. Yeah, so the lab is out. Okay, you got 2 weeks. That's due the day before your test. Please don't let it interfere with your studying. Okay, get on this ASAP, and if you have any questions, let me know. Okay, and when my Blackboard person gets back to me, I'll update you guys. But we're probably looking at a PowerPoint because that's nice and easy to upload, and it doesn't take much megage storage capacity. So, but other than that, we have the test in 2 weeks. You have your assignment 2 on electricity. That's due next week. And also next week there, we have quiz 4 will go out. And you'll have a week to do that. And I want you guys to, it'll be a precursor there to what the test will look like. Okay. But other than that, I thought test was Tuesday as well, 12 to 3. Can we do even a video? Yeah. We're probably looking at a PowerPoint. Like, I'll update you there, guys, this afternoon. I don't know why my Blackboard person didn't get back to me there yesterday, but I'll update you guys. But we're probably looking at a PowerPoint. And you know what I mean? You just take pictures of what's going on. Show me the results, these kinds of things. That's all we're looking for there, okay? The test is on Tuesday. This is our lecture time. This is the only time there that we're scheduled there to have a test per se. So the test will be 2 weeks today. Okay, at 12 o'clock. Does that answer any more questions? Anyone else got anything? No, it's all good. It's all good. If there's anything there that bothering you there, let me know. I'll be around there after class right now. So you guys are good. All right. And if you're not good, contact me and we'll get you good. Okie dokie. Let us go, shall we? I don't anticipate this one being very long. Okay. It's kind of a hodgepodge. Okay. It's interesting stuff. Sure it is. Promise. But we've got electromagnetism, electromagnetic waves, and we've got a bit of nuclear physics in here. So they're all kind of tied in together, and but we're going to kind of go off in different directions. And you'll see here that you've seen some of these things there before. Okay, so we'll go back to them. All right. What do hair dryers, automobiles, computer disk drives, elevators, generators, speakers, audio, videotape, and all these kinds of things, what do they have in common? Okay, they're all possible because electricity and magnetism interact with each other. And electricity and magnetism, electromagnetism. All right, and it's interesting how microwaves work, and we'll go through these things here. And again, you could write PhDs on every single slide. All right, we're just kind of skimming the surface here. Okay. Last week we learned about electric field. Okay, electric charges produce electric fields in the spaces around them. An electric field, regardless of its origin, causes a force on any charged particle. You remember there, a positive charge, okay? The force emanates from a positive charge, and the charge moves in that direction. A negative charge, okay, goes towards the negative charge, and the negative charge moves there in the opposite direction. And these magnets, they produce this magnetic field that we can't see. And you'll see here that this is your north, it's positive. Your south is negative. And you'll see here how the magnetic field emanates. That's how we know it's positive. And goes into there's your negative, right? And they just use some iron filings. Okay. And you can totally see what's happening here, this invisible magnetic field. Okay. Which the Earth has its own, right? That's how compasses work. And you'll see here that a magnetic field, regardless of its origin, causes forces on the poles of any magnet. And I have a really neat slide here that demonstrates the last point here at the bottom. A compass will align itself to a magnetic field. So right now, like if you had a compass, all right, just sitting here, it would align itself to Earth's magnetic field and start pointing north. Okay, which actually, if you can Google this and do a bit of research on it, the magnetic north is not true north. Okay, and you'll see there that the magnetic north, I think, was it 1,000 years ago? It used to be over Norway, and it's moving. And I think it was, or was it coming from the opposite direction? But anyway, the Earth's magnetic north moves. It's not stable. There's three facts here that I want to talk about when we're talking about magnetic fields, and we kind of introduced this there last week, and it's the right-hand rule. A moving electric charge produces a magnetic field in the space around it. An electric current produces a magnetic field around it. And you use the right-hand rule. And you see there your thumb is pointing in the direction of the current, and your fingers are showing you there the direction of the magnetic field. That's all that is. And this is, you see here we have 4 compasses. Compasses. You almost want to say compass, like octopi, octopus. Compasses, all right? And with no current flowing through it, right? And they're all pointing north. They're all pointing in one direction because they're using the Earth's magnetic field. But then, okay, now we've got an electric current going through. Okay? And the current's coming through here. And you'll see there that the compasses are now in this magnetic field. And you'll see how they're all pointing in this circular direction. Okay? Most applications of this phenomenon, they use coils. And to mimic this effect, they use what's called a solenoid. Long wires wrapped in the shape of a cylinder. And you'll see here, here's your solenoid. Okay? And it's often around an iron core, which greatly enhances a magnetic field. Okay? So all you're doing is you're just mimicking, okay, this magnetic field here. And it actually can get very strong. And this device is an electromagnet. It behaves just like a normal magnet as long as there's current flowing. So if current is flowing there through this wire, now you've got your electromagnet. Okay? But if you turn it off, if you turn the current off, the magnet turns off. So it's kind of good there. You, like a normal magnet there that, you know, we held in our hand as kids, you can't turn it off. It is what it is. It's a magnet. Positive, negative, north, south. But here we have a magnet, an electromagnet, that we can turn off and turn on. Okay? Fact number 2. A magnetic field exerts a force on a moving electric charge, which is just a current in a wire, not a stationary. Okay? And the direction of the magnetic field from a current carrying wire is perpendicular. And that's why I put this arrow in here. You see? Here's your direction of current, and there's your direction of the field itself. Okay? Not too bad. Number 3, a moving magnet produces a circular electric field, okay, in the space around it, forcing particles to move. So if you move this magnet around, you're going to get a circular electric field. Okay. There's a really good video here. It's this older guy, Dr. Julius Sumner, and I remember him there as a kid, and his videos are, I don't know, 1970s, like when I was your age there, in the late 80s there, we'd watch this, and the guy knows his stuff. I think he's long since gone, but his videos live on, and so have a look at this, and he's got other videos there as well, so maybe you might want to have a look at his stuff. And interactions between electricity and magnetism, the process of inducing electric current with a magnetic field is called an electromagnetic induction. And it's the whole idea of inducing means as you bring something closer to it, this new object induces an effect on the other object. And that's what I want you guys to see there in the video. It's not bad, okay? And all that is required is that the magnet and coil move relative to each other, okay? And you will get this induction effect. Here's a recap of facts 1, 2, 3, what we just talked about there. You guys can have a look at that. You'll need these there for a test or something, so it's easier. It's good just to have them there to recall, okay? Like the nice thing here is you really don't have to remember everything. You have your testing situation. You'll have everything ready to go. And so not too bad. Eyes, radios, televisions, radar, x-ray machines, microwave ovens, heat lamps. What do all these things have in common? EM waves, electromagnetic waves. Oh, that's horrible, man. Why would you do that? Ugh. As the name implies, electromagnetic waves involve both electricity and magnetism. And electromagnetic waves, transverse waves consisting of a combination of oscillating electric and magnetic fields perpendicular to the wave direction. Nothing new there. Electromagnetic EM waves there, they differ from mechanical waves. This is a good one to know. Great true or false, or great multiple choice. Electromagnetic waves are a combination of two waves in one. Okay? An electric field wave and a magnetic field wave. And if you take away one of those, the whole thing disperses. You need both of them there in order for an EM wave to exist. And electromagnetic waves do not require a medium. So these ones here, electromagnetic, they can travel through space, through a vacuum, okay? And but remember, sound waves do not. They need a medium to carry them, all right? We've seen this there before, okay? These are all the different waves, the wavelength, even like you'll see sizes of the waves here, generally speaking. Like radio waves there, they can be a kilometer long, one wave. And you'll remember there, wavelength, all these kinds of things. Microwaves, okay, here we're talking centimeters. Infrared, it gets smaller. And your visible light is in here, okay, and ultraviolet. And you'll see here that the shorter the wavelength, the more energy is involved per length, right? Because the energy of a wavelength is going to be the energy of a wavelength. If it's 1 kilometer long, okay, there's one wavelength. That's why the radio waves aren't dangerous per se. But now you start getting into UV light, X-rays, gamma rays, where like gamma rays here, we've got 10 to the negative 12. Like we're over a billion, over 100 billion wavelengths in 1 meter. So you've got a whack load of energy in a small amount of space. So that's why these guys here are dangerous. All right. These waves travel at extremely high speed. Their speed in a vacuum is called the speed of light. That's what this is. And we use this with the letter C. And that is from probably the most famous formula in physics, Einstein's theory of relativity. E is equal to mc squared, mass times the speed of light squared. And we take the value for the speed of light in a vacuum at 299,792,458 meters per second, or just to keep it easy, 3 times 10 to the 8 meters per second. 300,000 meters per second. Or sorry, 300 million meters per second. All right? So that'll be 300,000 kilometers per second. So that's what this is. There's the speed of light for you. You're going to need it there. There is a little bit of math in this PowerPoint, but really not much. You've seen this formula there before. Okay. An FM radio station broadcasts electromagnetic waves with a frequency of 100 megahertz. Mega. What is the wavelength of a wave? So the prefix mega stands for a million. So therefore, I gave you 100 megahertz. So therefore, the frequency is 100 million hertz. Okay. So here's your formula here. All right. And solve for wavelength. Okay. So C is equal to F divided by our frequency times wavelength there. We just flip it all around and solve for wavelength. And your wavelength there is 3 meters. So not too bad there. New formula, but really it's an old formula. Okay. So C just kind of takes the place there for velocity. That's all it is. Things to note about EM waves. Electromagnetic waves are a form of energy, and it's energy needed to produce these EM waves, and the energy is gained by anything that absorbs them. So you need energy to make it, and this energy is definitely absorbable. Okay? Think X-rays, definitely absorbable. And the transfer of heat by way of radiation is one example. When you're sitting out in the sun, you're receiving there the sun's radiation, and you get your little bit of vitamin D, and it warms you up. Heat transfer. Radio waves, the lowest frequency They can be 100 hertz up to 10 to the 9 hertz. Just massive, massive. Okay. Most frequencies are given in kilohertz or megahertz. I'll definitely give this to you on a test. Kilo means 1,000. So if I give you if something is 10 kilohertz, that means it's 10,000 hertz. If something is 1 megahertz, mega means million. So 1 megahertz is 1 million hertz. Okay? Just know that. You'll see that again. Okay? Microwaves. Very interesting stuff. I guess that there was a study done, I think it was probably 2 or 3 years ago. What is the most important piece of kitchen equipment? And resoundingly, it was the microwave. People use their microwaves every day. I think I've already used it 5 or 6 times there. Okay? And just the whole idea of how water's based on it's a polar molecule. But we'll get in there on how it actually works. One use of microwaves is in communication. Okay, Bluetooth, Wi-Fi, they rely on microwaves to send and receive signals. Okay, radar. Okay, because microwaves are reflected by metal. Like, you know not to put metal things there in a microwave because it'll just go boom. All right, it'll reflect it and it won't go through the food down to the bottom plate, and then it goes back up again. If there's a piece of metal in there, it stops it. So because microwaves are reflected by the metal in ships, which is the echolocation using microwaves, even Doppler for weather tracking. Okay, so radar is just using microwaves there. Echolocation, Doppler, or radar effect. You know, when you go to the weather network there and you'll see them like this, right? And you'll see them tracking a storm. That's all they're doing. Microwave ovens penetrate food and raise the energy of the molecules directly. And how it does that there, the electric field of a microwave exerts forces on 2 sides of the water molecules. And basically, microwave is just a machine that does this. Heating up your hands. All right? It's friction. And you're taking the water molecules, which one side is negative, oxygen, and then the other side is the hydrogens there, right? That's your positive end. And all it's doing is it's just flipping them around very fast because it's changing, right? Well, here, I'll just show you here. These forces are in opposite direction, and they twist the water molecules. Because the electric field is oscillating, okay? The molecules are also oscillating. They're flipping back and forth. The water molecules in your cold chicken sandwich, and after about 45 seconds there, those water molecules have been flipping around, and now you have a warm chicken sandwich just because of friction. Okay, so because the electric field is oscillating, the molecules are twisting one way and then the other, and increasing their kinetic energy, which we turn into heat. All right. Infrared, okay, also called IR, and this occupies the region between microwaves and visible light. So let's go back up here. So, okay, there's your infrared right there. And I think it was here. And infrared radiation is ordinarily the main component of heat radiation. It's also used in wireless remote controls. Okay, even for your laptop computers. There's your IR. There should be an IR on the side of your computer there. Or maybe it's been outdated, I'm not sure. Electromagnetic waves there for visible light. Visible light is a very narrow band of frequencies. Okay. Next week there, when we get into, I actually have a picture of the eye, and we're going to see, because next week there is all about light. That's why I'm not really going too heavy into it right here. But light coming into the eye and how it gets flipped and then transmitted there to the brain, the optic nerve, and all this. So we'll go into a little bit of biochem there next week just to show you about the eye. All right, your rods and your cone cells, they're very sensitive there to the electromagnetic waves. in this particular band. Like the electromagnetic spectrum is yay big. X-rays, gamma rays, radio waves, infrared, visible. And the visible light is only a very small amount. Okay. The rods and the cones, they respond to visible light, okay, by transmitting electrical signals to the brain. Okay. Visible range of some animals, such as hummingbirds, bees, extends into the ultraviolet. Okay. Some flowers that seem plain to human are quite attractive. What have we got here? Where's my picture of my marigold? Maybe it's down further. Like a flower that looks pretty boring to us just might look incredible there to an insect or an animal that can see in the ultraviolet spectrum. And I got a picture of that there. Okay. UV light, UV radiation, ultraviolet. Okay. Just above the frequency of violet and extends into the X-ray band. About 7% of the radiation from the sun is UV. The ozone layer, oxygen is O2. There is an O3, and it's a strange one. It's 3 oxygens together, and there's kind of a resonance structure similar to benzene. Okay, this resonance structure of these electrons moving around, and ozone is known to prevent UV light from entering into the Earth's atmosphere. And I was down in South Africa, this would be 10 years ago or so, where the ozone layer was, I think it's coming back. I know when I was a youngling there was big talk about the ozone layer being depleted there at the poles, especially around South Antarctica. And I think it's coming back now, but never had a sunburn like that. It was 10 minutes in the sun, and it was bad. So UV light, yeah. Oh yeah, here's my picture there, the same flower. You'll see there that this is what we see. This is what a bug sees. And to a particular species of bug, this could be the most delectable thing ever. Okay? And just different ways of looking at it. Some kinds of invisible ink can be seen under a UV lamp. You can even take lemon juice. You know, as a kid there, you play with, invisible ink. All right, you can make secret messages, these kinds of things. Sterilization of hair and medical equipment. Okay, they use that UV light there. And insects can also see into the UV spectrum. So this is what a bug would see there. Okay. X-rays. X-rays are very, very good for looking at hard tissue. We use an MRI, magnetic resonance image system there for looking at soft tissue. Okay, but X-rays are great for looking at hard tissue because of calcium. Calcium is relatively, it's bigger atom. Okay, it has an atomic number of 20. Okay, but then you look at carbon, oxygen, they're just small, 6, 8, and 1. All right, but we use X-rays there to look at hard tissue bone structure. Okay. X-rays, and we'll throw gamma rays in here. We'll talk more about gamma rays in a little bit here. These are the most damaging, okay? Harmful because they are ionizing radiation. Radiation that produces ions as it passes through matter. And this is the problem here when these massive amounts of energy flowing through, and what happens is it basically disrupts the medium that it's going through and causes ions and causes disruption, okay, as it's flowing through something. And it's that can be carcinogenic, you know, cancer causing, disease causing. That's where the fatalities come from, is the damage that this stuff does as it passes through. Such radiation can kick electrons out of an atom, leaving a trail of freed electrons and positive ions. And that's where we get into these guys here, these free radicals. Okay, these are you'll notice there you want to take, free radicals are these atoms, high energy, shouldn't really be there. Okay, And that's why we eat purple kale and all these basically colorful vegetables, because we blueberries, these kinds of things, because they are full of what's called antioxidants. And antioxidants are these cushiony molecules that are able to absorb the high energy from these free radicals. Because these free radicals, if they're let loose in our body and they start bumping into a cell that is in the middle of mitosis, right? You know, the DNA, it's all wrapped up nice there in the chromosomes, but then it's got to kind of unfurl itself, and it's just a massive molecule, DNA. And if it's unraveled a bit, right, for the purpose of mitosis, and then one of these free radicals comes in and bumps it, well, it's such a complicated process. One mistake, and now your two daughter cells are not identical to your parent cell. All right, and that's where you get cancer now, because now these things are kind of running out of control with no guideline, right? So we don't want those free radicals around. Have your antioxidants. Gamma rays here, these are the highest. These are the most dangerous, okay? And the wavelength of a higher frequency gamma radiation is about the same distance to the diameter of an individual nuclei. Okay, so that's how small these are. So this, in the same amount of energy in this wavelength here, that's a 1 nuclei long, is the same amount of energy that's in a kilometer long radio wave. Okay, so that's why these guys are tough. Gamma rays are emitted in a number of nuclear reactions. We're going to talk about some of these: radioactive decay, nuclear fission, nuclear fusion, to name a few. So we're going to talk about these three there, okay? They're not bad. Have a look at this one, smoke detector. It's really good. If you don't have one in your house, get one. And I mean this morning. Sorry, it's 12:40 this afternoon. If you're renting a house, make sure that your landlord has one of these in there. You also need a carbon monoxide detector by law. So if there's any discrepancy on that, you make sure that you guys have one, okay? Crazy important. And you'll see there that they use radiation. Yes, radiation in your smoke detector. All right? So have a look at that video. It's a good one. A little bit of atom review. Nucleus contains two kinds of particles, protons and neutrons, which physicists now, we just get lazy and we call it nucleons. Okay? Because the proton and the neutron, they have exactly the same mass. Okay, 1.66 times 10 to the negative 27 kg. All right, so the neutrons and the protons weigh the same, and it takes about 1,840 electrons to equal the mass of one of them. Okay, and you'll know there that the proton has a positive charge, the electron has a negative charge, and there's some machine there. I don't know what it's doing. All right. Now the neutron, no charge. But is it really that ineffective of a nuclear particle? Well, it's really not. It's really not that effective. It's actually very effective. It's a whole branch, okay, nuclear chemistry. You see, like normal chemistry, the chemistry there that you're doing right now in 1009, that's all electric chemistry, electron chemistry. The whole idea here is we take sodium metal, which is very dangerous stuff, and you take chlorine gas, which is extremely dangerous stuff, and you mix these two together, and you get sodium chloride, which is just amazing on your spaghetti, salt, all right? And what's gone on there is just the transfer of electrons from the sodium atom to the chlorine atom, okay? If you're not following this, we'll shoot me an email. We'll get you guys sorted. But that's electron chemistry. That's how the whole world works. But then we also have nuclear chemistry, where this is kind of chemistry that's not involved with the electrons moving from one atom to another. This is only dealing with stuff that's going on in the nucleus, nuclear chemistry. Okay? If electrostatic forces, they keep opposite charges apart, right? You remember there last week there, we had two positive charges come and they didn't like each other. We have two electric charges come together and they didn't like each other. We have a positive and a negative, they come together. They like each other, right? So you have to think, what charge is the nucleus? Well, the nucleus has protons and neutrons. Neutrons don't have a charge. So if there's only the only charge that's going on in a nucleus is protons, so then a nucleus is positive. Would you agree? Good. Thank you for that. So the nucleus is a positive beast. So you got all these positive protons in there. But wait a second. Like charges don't like each other. So how do we, okay, I can get all these protons into a nucleus, but how do I keep them there? Because they don't want to be there. They're just going to fly apart. Well, and that's what it says right here. Protons should be flying away from each other. You're bringing all these protons in together. They should be flying away from each other, but they're not. Okay? And we call this, what keeps all those protons together is what's called the strong force. And I apologize, I didn't make the name, but that's what it is. It's a silly name, but it's an incredible idea. And they don't really kind of understand what the strong force is per se, but there's something there that is keeping that nucleus together, keeping the protons together. All right? And then we have what's also called the electric force, which is the protons trying to get away from each other. Okay? So something is keeping them there. That's the strong force. And then the electric force is the protons trying to get away from each other. And you'll look here by the size of the arrows. The strong force, this is a massive force. The electric force, depending upon the atom here, all right, is, if you look at these two atoms here I have a smaller atom and here I have a massive atom. Okay, orange being protons, blue being neutrons. Okay, and you have a look here. This proton is probably almost touching that proton there. And look, it's only one neutron away from here. Okay? So you need pretty good strong force to keep these guys together because the protons are almost kind of touching. Well, when you get into a bigger atom, you're going to have more neutrons. So you've kind of got more space in between proton and proton. I'll show you guys more examples of this here, but you'll see here that your electric force for a bigger atom is actually less than it is for a smaller atom because these guys here are relatively close together. Where these guys, the protons here, I know it looks like they're all touching and this and that, but they're kind of more spaced out because you have a lot more neutrons in a bigger atom. But we'll get into more of this. For smaller atoms, here we have strong force versus the electric force. So the protons are in close proximity to each other, and this tends to be a stable. And the strong force there for smaller atoms is pretty strong for a smaller atom. That's why smaller atoms like carbon, nitrogen, oxygen, these ones here, they're stable. And now what do I mean by stable? Well, they're not breaking down. They're not decomposing. They're not like this all the time, right? Okay? If you had an atom that's like this, not stable, and because the strong force is not keeping your atoms there, well, then you're going to have a popcorn effect. All right? Your atom, your nucleus is going to disintegrate. And we'll get into that. What's the result of an atom's nucleus disintegrating. It's interesting. For larger atoms, the strong force versus the electric force, and you'll see here that there is proton shielding due to the increased number of neutrons. Okay? So what happens is bigger atoms tend to be less stable. Okay? Smaller atoms, all right, they're pretty stable. The strong force there is doing its job. Smaller atoms, stable, strong. Now you get into bigger atoms like this, and they become more wonky. Okay? They're less stable. Okay? And because you've got these protons are shielded, all right, because of more neutrons there, so it's not as stable. You might have a region of instability within the nucleus itself. So therefore now this bigger atom is more prone to breaking down. And what that is, the end result of an atom breaking down, I'll show you there in a second. You'll see here that neutrons are not really neutral. They don't have a charge. Protons are positive, electrons are negative. Where these guys come into play is isotopes. And you'll remember what an isotope is, right? It's an atom with the same amount of protons but different amount of neutrons. Say that again. An isotope, probably haven't heard that word there since last semester. An isotope, two atoms, and you can look at the screen right here. I have hydrogen, deuterium, and tritium. Really, it's hydrogen, hydrogen, and hydrogen. How do I know they're hydrogen? Well, hydrogen, I got one proton. Here is deuterium, all right? How do I know that this is hydrogen? Well, it's got one proton, but you'll see here, it's also got a neutron. So this is hydrogen because it has one proton. Because there's only one atom, one kind of atom that has one proton, and that's hydrogen. But you see this one here is heavier, okay? All right, so this is hydrogen 2,1, and they actually have a special name for it there called deuterium. And then we look at this beast here. Well, how many protons does it have? Well, it's got one proton. Okay, so one proton's got to be hydrogen, which it is. But you'll see there that this guy has 2 neutrons in its nucleus. So now its mass is 3, atomic mass of 3. You'll notice there my atomic number is 111, doesn't change, okay? And these 3 here are all hydrogen, but you'll see this is hydrogen with a mass of 1, this is hydrogen with a mass of 2, this is hydrogen with a mass of 3. Their nuclear chemistry is going to be different. All right, and apparently this stuff here is worth more than gold. All right, they use this there in nuclear reactors. Okay, there's your isotopes there. I just kind of went into them there. Just remember, isotopes, the same atom, different molar masses, different masses. Okay, same atom means same number of protons. So boron and boron. Okay, same banana, but you'll see here that here I have boron 10, 5 protons, 5 neutrons, and here I have boron 11. It exists both in nature. They're both good. All right, it may not be 50-50. It may be 80-20. It may be like if you go back to here, look at your percentages. 99.97% of all hydrogen in your water, in my horrible cup of coffee here, is this. 0.01%, there will be some deuterium in your water. And then here we've got 10 to the negative 17, very, very small amounts, but it is in here. Okay, so the different percentages, okay, they will vary from element to element. Okay, what do we got here? The different isotopes on an element have the same chemical properties that will have different nuclear properties. Like, for example, most nuclear power plants rely on splitting of uranium-235 nucleus. Uranium atoms with a mass number, okay, a mass number of 235. Uranium-238 does not work. So you'll see there, I have two isotopes of uranium. I have uranium there with 235 nucleons, and then we have uranium-238 nucleons, right? So 92 protons for both, but they will have different number of neutrons, right? And therefore, for in nuclear power plants, they only use this one. Most of the 118 different elements, they have several different kinds of isotopes. Some of them have 2 or 3, okay? And what do we got here? Hydrogen has 3. We just saw them, okay? And others have more than 20. Iodine, silver, and mercury. Lots in there. Okay, so there's no rhyme or reason to it. I would never ask you there to know any type of isotopes. But if I give you an example there, like the hydrogen there, it'll make sense, right? Isotopes, same number of protons, same element, different number of neutrons. Okay. Each different isotope and element is designated by its mass number. The most common isotope of helium is 4, and this is we call helium-4. So there's 2 protons. Helium is number 2, so it has 2 protons and 2 neutrons, right? But there also is a helium-3, 2 protons and 1 neutron. And they use this A, Z, and N, okay? Just being able to figure out, if I give you mass number and protons, you can tell me how many neutrons there are. Just subtract one from the other. Okay, that was all done there last semester in chemistry. Going back into atomic stability, okay, neutrons to protons, okay, we're looking at about 1 to 1 for small, okay. For bigger atoms, you're looking at 3 to 2. And you look here, the stable isotope lead-208 has 126 neutrons and 82 protons. Okay, so it's about 1.5 to 1. Okay, which is 3 to 2, about. So this is a stable atom. When we start getting outside of that, okay, that's where you start to see this instability within the atom. And if an atom is unstable, that means that it could bust open and break. So a part of this atom, unstable atom, is going to break off like a meteor off of it. And what's left? So in this little piece that breaks off, all right, it's going to fly off and leave what's left. So now we've got a different number of protons that are left here, so we're actually going to get a new element. I'll show you this right here. You guys want to see what happens when you break the strong force? That's just how strong is the strong force. Okay, there's so much energy trapped in these nuclei. And if you break them, that energy comes out. And boom. That's what's going on. So you look at the stuff there with an atomic bomb. They're generally not using stable. They're using unstable atoms. And when these unstable atoms, which aren't really that difficult to break, that's the result. Okay. Radioactivity, also called radioactive decay. Anyone here ever... I did an undergrad in archaeology, and fascinating, and just the whole idea of radiocarbon dating, the ability there to analyze a piece of cloth or something there found and to give a relative carbon dating and how old this artifact would be. It's incredible, it really is. And we use isotopes, okay, to determine this, and we'll call them radioisotopes, okay? And it's all just, the whole process is these atoms if they're deemed to be a little unstable, then we can actually measure mathematically their instability, and every atom will break down at its own rate. So just like the periodic table is all organized by protons, right? Different protons, different electrons, different chemistry. We've got our columns and our rows and everything, and everything has its own pattern. Well, all atoms will break down according to their own pattern, and we can analyze that to determine age. When an unstable nucleus decays, particles and energy called nuclear radiation are emitted. Okay, and there's 3 types of radiation here that we're going to talk about. Alpha radiation, alpha particles. Okay, beta radiation, beta particles. And then we've got gamma radiation, no particle. Let's say that again. They're all radiation, alpha, beta, gamma radiation, but there's only 2 of them that we actually call a particle. And if something, we're calling it a particle, that means it has mass and occupies space, right? So alpha particle, we'll show you that. A beta particle, we'll show you that too. And then there's gamma radiation, which is just EM waves. Okay. Very good. What do we got here now? So alpha particles. You guys will have seen this there before. Okay. All it is just a helium nucleus. Helium atom, 2 protons, 2 neutrons. There's your nucleus. And then I have 2 electrons running. That's a helium atom, right? Well, if we just take away the electrons, throw them over there, now I just have a nuclear beast with 2 protons and 2 neutrons. No electrons. So what's my charge? It's +2 because there's no electrons flying around to balance out the 2 protons in. So this is just a ball, 2 protons, 2 neutrons with a charge of +2. Okay, and it's a helium nucleus, but when we're talking about radiation, we're talking about the alpha particle. Okay, an alpha particle has an electric charge of +2, an atomic mass of 4. Description there, high energy. Okay, symbol is there. Blow this up a bit, eh? No, it doesn't want to. There we go. So you see here, symbol, okay, is 42He. The mass, 4 nucleons. Okay, charge +2. How strong is it? You can stop this radiation with a piece of paper. So it's not too bad. All right? Not great, but not too bad. You can stop this with a piece of paper. Okay? Beta particles, a little bit stronger. Okay, second type of radioactive decay is called a beta particle. This one here is going to seem a little weird to you, but as I said there, the physics and the chemistry, the deeper you go down the rabbit hole, the stranger things get. And we're not going that deep, but you're going to see here that this is kind of a weird one. This is a particle, and it has a mass. All right? And it has a mass of about an electron, and we're going to call it an electron. All right, so this unstable molecule, this unstable atom, and part of it breaks off, and in this case here, it's a high energy electron, and you'll see its symbol there, -0.1/E. I'll see if I can blow this up a little bit, right there. Okay, you guys can see that. And it's about this, it's relatively small compared to the alpha particle. As we said there, it's basically an electron. That's what a beta particle is. This one here has a charge of -1. Now, This one here will go right through a piece of paper, but it can be stopped by a piece of aluminum. That's about 3 millimeters thick. So it has more penetrating power than the alpha particle. Okay, not as much as gamma. That's what we're going to get to there next. Okay, so an alpha particle, charge of +2. Beta particle, okay, it's an electron, charge of -1. It can go through paper, but a piece of aluminum will stop it. And gamma, no particle. It has no mass, unlike the other two. Okay, it has no charge, like the other two. All right, but it's mucho high energy. Okay, this thing can go through cement. This thing can go through houses. Okay, and very, very high energy. And its symbol is this gamma symbol. I don't know if you guys can see that there. It's right here. Okay, you'll see them there on the weekly questions. All right, and this one here, a thick block of lead is the only thing that can stop this. So very, very, very high penetrating power. Okay. Gamma rays are the most penetrating of the three, and you'll see here that this is kind of contradicting itself. But what I'm interested in here is this was a piece of paper. Alpha particle there would be stopped. Okay. The beta particle is stopped by a thin piece of aluminum. A little heavier, denser material, right? Piece of paper is very porous. And then even lead. Okay, lead is the only thing there that can stop these guys. And even in some cases there, depending upon the frequency or the intensity of the gamma particles, lead won't even stop. So that's that one there. Now, the whole process of producing alpha particles or producing beta particles or producing gamma particles, okay? This is what happens here. Have a look here, alpha decay. Just the process there of nuclear decay. And you have this molecule here, polonium. And please take notice, 84 protons, that's your atomic number, 210 is your atomic mass. So if you subtract 210 from 84, you should be able to tell me how many neutrons are in this. Okay, remember that there from last semester. So what happens here is you have this big molecule, and it's wonky, and it's unstable. And then what happens is a part of it breaks off with those exact same sound effects. And what happens here is an alpha particle will break off. All right? And it'll take 2 protons and 2 neutrons with it. So now, polonium, which is the only atom that has 84 protons, has now lost 2 protons. So it ain't polonium anymore. This is now lead. So what we've done is we've actually created a brand new element in this process of decay. All right? And you'll notice, you'll need this there for your weekly questions. You'll notice that everything adds up. The right side balances the left. Here I have 84 protons here. Well, on the right side I have 82 and 2. Everything has got to add up. Here I have 210 as my mass. Well, here I have 206. This one here has to be 4. So if I give you this and this, you should be able to tell me what this is. Or if I give you this and this, you should be able to tell me what element this is. Because you see 2 plus 82, 84. Okay, then you go to your periodic table. What's the only element that has 84? Aha, that is polonium. Answer, polonium. So just remember, left side equals the right side. Have a look at beta. This one here, don't let it confuse you. It's the exact same thing. And this is a good word, transmutation. the creation of a new atom from nuclear decay. Here I have iodine. I got 53 protons, a mass of 131. And this thing will break down. And in this case here, a beta particle is produced. Now the numbers are going to seem weird. I'm not going to go into the physics behind it. But have a look here. 53 protons on this side. Well, here 54 protons here. So this actually went up a proton. But then here we have our beta particle, all right, that is flying off into space. And you'll see there that just look at the mathematics. 54 minus 1 is 53, which equals here. Left side, right side has to balance. Look at 131, 131, 0. Everything is balanced, okay? And the significance of what goes on here, you could sum into what's called nuclear fission. Okay, this is what goes on there in a nuclear reactor. Okay, and what they'll do is they'll send neutrons and they'll bombard these unstable atoms. Like look at this one. This is uranium-230, 235. Uranium, 92 protons. It's the largest naturally occurring element there that we have. Okay, just a massive, wonky beast. Just massive. And what they do is they'll fire a neutron at it. And what'll happen is that'll make these unstable atoms, who are already unstable, it'll now you'll start creating more atoms that are unstable. And you see here it hits here and then it breaks. What does it break into? It breaks into krypton and it breaks into barium. Two brand new elements. And the neutrons are still out there, and what these neutrons end up doing is they go and hit others, and hit others, and hit others. And this is where you get this chain reaction. Okay? And you get all these new elements being made, and a lot of energy being released. Okay? So that's nuclear fission. That's what goes on in a nuclear reactor. Here's your chain reaction, just to show you there. Neutron comes in, and then just cascading effect. Okay? Fusion, okay, fission is what goes on here on Earth in a nuclear reactor. Nuclear fusion, okay, this is where two usually small nuclei come together to make a bigger nuclei. So you think about it, you have a hydrogen and another hydrogen right here. Here I have hydrogen, and here I actually have deuterium. 1, 1. A star will take these two atoms and put them together. So look what we have now. We have helium. And in this process, the star releases energy. And that's how we get our energy there from our sun. Okay? Fusion fuses atomic nuclei together, while fission splits them apart. Okay? And it makes you wonder. Here I have a hydrogen, and a hydrogen came together to make a helium. What if I had a helium and a helium come together? Could make boron. And you have to think, were we all made in stars? Are the carbons, the oxygens in our body, the nitrogens in our body, the calcium, where did all that come from? Well, the hydrogen and hydrogen came together, and then two heliums and two heliums came together, and then two carbons and two carbons came together, and that's how you make bigger atoms. Measuring, okay, we can use a Geiger counter. Okay, I'm not looking there for too much, but just being able just to recognize that a Geiger counter there is a device that measures the amount of radiation by producing an electric current when it detects a charged particle. And that's all. Geiger counter there. Now, a little bit of mathematics here. Here, when we're talking about measuring the age, the antiquity of something there, we deal with what's called the half-life, okay, of an element. The age of these materials can be determined using a half-life. The number of half-lives is the amount of time that has passed since the isotope began to decay. So basically what we're talking about here, these unstable atoms, they all have a half-life. Now, what does half-life mean? It's the amount of time it takes for half of that atom amount to break down. So half of it breaking down, how much time did it take? That's an element's half-life. Okay? All radioisotopes spontaneously decay, as I said earlier, and they do it at their own specific rate, individual to that element. Okay, so every element will break down in its own rate, and we have that measured. Okay? Carbon-12 makes up most of the carbon on Earth. But there is a radioactive carbon that exists in all of us, everywhere, all the time. And it's in there. And it's only about 0.1%, but we can measure this. And it's present everywhere. So we can measure how much carbon-14 is in a living as opposed to something that's long past, and how much carbon should there be, as opposed to how much carbon is in the carbon-14 is in there now, and we can calculate how much time. I'm going to show you how to do that. Carbon-14 has a half-life of 5,730 years, meaning that after that amount of time, let's say I have 50 grams of carbon-14. 50 grams of carbon-14. After 5,730 years, I'll only have 25 grams of it left. That's what half-life means. Okay? So, scientists use this half-life to determine how old things are. The half-life of a radioisotope is the amount of time it takes for half of it to decay. And you'll see there, that's how it goes. Okay? After a certain amount of time, it's half, and then half, and then half, and then half. You'll see there, you'll never really reach zero. Okay? Each of these guys here is just some examples here. Hydrogen has a half-life of 12 years. Lead, 10.6 hours. This isotope of lead. Carbon-14, 5,700 years. This isotope of polonium has a half-life of 0.5 seconds. So if I had 50 grams of it, okay, after half a second, I'd have 25 grams. After another half second, I'd have 12.5 grams. And we'll show you guys this. I've broken this down. How do you guys do this? And this is, I've been doing this there for, I don't know, teaching this stuff there for a while. And I've gone through different ways. And this way here works every time. So have a look here. How much of 120 grams of hydrogen-3 would remain after decaying for 48 years? So I start off with 120 grams and let it sit there for 48 years. The half-life of hydrogen-3 is 12 years. So after 12 years, half of my hydrogen is gone. I want to know how much hydrogen is left after 48 years. Well, I go mass, okay, grams, and I start with 120 because that's what it says. I started with 120. And then my half-life, which is 12 years. And then I go total time, 48. So, because here we're going to start this way. Another question might be, I might ask you to go backwards. And we'll show you this there. So as long as you have mass, your half-life, and your total time, you can't go wrong with these. So you put your total time in down here, well, whatever the time is, 48 years. I start off with 12 grams. And one half-life is 12 years. So what I do is I put in a loop. That's one half-life. 2, 3, and 4. So there's been 4 half-lives. Okay? 12 years, 12 years, 12 years, and 12 years. So 4 times 12, 48 years. Okay, that adds up to this. Okay, so I'm good. And when you're measuring grammage or mass, you start with 120. After one half-life, you have 60, 30, 15, and 7.5. So at the end of 48 years, you'll only have 7.5 grams of this hydrogen left. Please, when you're measuring grams, count the tops of these. All right? One half-life, okay? Because if you're putting your 120 grams down here, 120, 60, 30, you're going to get an answer of 15. It doesn't work. Okay? So if you guys do it like this, you'll never go wrong. Another example here. In a 100 gram sample of an isotope with a half-life of 10 years, decays for 20. How much mass will remain? Same question, just different numbers. Okay? Look at this one. I just made this up. Kimranium 456 has a half-life of 5 hours. How many hours are 4 half-lives? So in this particular question here, we're not looking for grams. We're just looking for how many hours are in 4 half-lives. 4 times 20 is 20. This one here, an isotope of lead has a half-life of 11 minutes. What fraction of the leaden 194 atoms would remain after 44 minutes? So here, I didn't even give you grams. I gave you percentages. Okay? Still works the same. I didn't give you an initial gram mass at the start, so you just use 100%. I had 100% of this. Okay? After one half-life, 50%, you just, and all this, and at the end of it there, you'll get 6.75%. Let me know if you guys have any issues to this. I'm kind of flying over this, but I hope you guys are doing all right with all this. And you guys will see questions like this there on the weekly. They're not bad. I know they kind of look freaky, but they're not. Like, let's say I gave you this, okay, and I move that? Why won't let me move that? Wonderful. Okay, so if I gave you this right here, potassium 4219, and I gave you this is a beta particle, right? I might ask you, what would this element have to be? Well, okay, well, the top has to add up all across. So here I've got 42 as a mass number on this side. Well, I don't have anything here. So that means that this number here has to be 42. Well, here I've got 19, and this one here is -1. I know the math is, it's kind of, no, I'm not going to go in detail about a beta particle, but you'll see here that this number here has to be 20. 20 minus 1 is 19, all your numbers. And then how do I know that this is calcium? Because initially you're going to have 42 over 20 because of the mathematics. What element is this? Go to your periodic table, which you guys all have. What's the only element that has 20 protons? Has to be calcium. Neutrons can change. There's only one banana with 20 elements, or 20 protons, okay, and that's calcium. Here, the same thing. I give you this, you got to figure this out. Well, 94 protons on this side, I have 2, so therefore this has to be 92. What's the only element that has 92 protons? Uranium. And it's the same thing there for this one here. So this is what I'm, try these out. Shouldn't be too bad. And let me know what you're thinking. Any questions? Is anybody even still there? Oh, wonderful. There you are. But that's all I got there for today. I hope you guys are all well. Try some of these questions out. You guys are keeping in good contact. Ask as many questions because in 2 weeks the whole thing is over and then y'all are free. And just keep at it. Yeah, I hear you, Nicole. Yeah. You guys are good. Have a great day. Get out of here. Stay in contact and be well. I'll post this there to YouTube in 2 shakes of a lamb's tail. Thanks, guys. Have a great day.
Ian. I have another question.
No problem. Here, let me turn off the recording.